Hey everyone, welcome to another tutorial on this Autograd from scratch in C. So what we did in previous one is we just went ahead and created our tensor matml forward function, which did a lot of different things, which actually created a computational graph for forward function. And now we need to build tensor matml backward. What it does actually, it takes the gradients of our existing tensor. Um, it takes the gradient of loss with respect to the parameters, and it just populates the gradient parameter inside our tensor structure, right? So yeah, this is what we are going to do. Remember, what we are doing actually is, let me show you the main file for now, how it looks like. So we're able to train our model first thing, right? What we did is actually we just created our framework right from the scratch, creating tensor abstract, creating multi-head attentions, creating layer norms, creating feed forward networks, and then we went ahead and written manual backpass. Once when we run the forward pass, and then we just created logic for backward pass as well for all the layers which I mentioned, right? Taking the gradients, using the chain rule, partial derivatives, updating the parameters, uh, and we saw that our loss was decreasing. The next step in our framework was creating an arena and not using malloc. So we created a giant array, contiguous array of some static size, and we borrowed the tensors from that arena, right? Chunk after chunk, and then we returned the pointer for every byte that has the last byte of offset, right? And then we went ahead and at once finally in our main function we just initiated the weights, and borrowing the space for every single tensor at once, not several times using mallocs. And then we have successfully trained our model, and we saw that loss was also decreasing, right? Now, we wanted to write our own autograd. What it does basically is it just creates a computational graph on the forward pass, and then populates the gradients, flow back at the backward pass, right? So the main idea over here is what we did is actually is the main idea is uh, you know tensor matml, softmax, tensor addition, scalar multiplication, and exponential. These are all the things that are the components, right? And multi-head attention, feed-forward neural networks, and layer norms, these are actually the layers. So we don't have to do anything with the layers. What we are doing actually, we are setting up the foundation for autograd in case we let me show you let me show you how the tensor file looks like. So these are actually all the important methods which we need to work on. Yeah, these are all the ones, right? So we'll be making our changes with respect to them. We'll be creating forward and backward right functions, which works with our autograd. And once this is done, the multi-head attention, the layer norms, and few neural networks, they will be actually aligned with our autograd thing. So we need to work on these basics. These are the components which build the large parts, and large parts are the layers, right? So we need to build our components. Once we have successfully done that, it's all about chaining them with the layers, right? So we don't have to do transformer backpass, right? Backward. All we have to do is we need to write tensor matml backpass, tensor softmax backpass, and yeah. So I hope I'm able to convey the idea. So enough of the rambling. Let's go right into the code now. Okay. All right. Fine. In case if I see, yeah, let me just see this. So here I'm using tensor create new. So I'm done with the tensor create thing, right? I have modified the tensor create function, and this will work just fine. So in case if I want to see, let me pull up the test file. So this is my tensor, a new tensor structure. Previously it was like this. So tensor.h previously was something like this. So we had only shape, stride, and dim and data, and now we have these parameters as well for autograd, right? So we did the necessary changes with the tensor structure. We have done the necessary changes with tensor forward function, and now we need to write tensor backward. And the file that I just shown you, tensor.h, Yeah, this also, these are the functions that need to be modified, right? Like this value backward, and we'll be seeing that, and by modifying I means that we'll be creating the computational graph on forward pass, and then we'll be writing, once we create the computational graph, which will take care of all the uh, which silently basically builds a graph under the need. For example, let me show you this thing actually, so how it works. So need to pull up um, my sketchpad. uh, mm, so let me show you what happens underneath. So let's say, for example, I have some tensor that is called x, and some tensor that is y, and I took the product of these two using a matimal operation. I'm denoting this with and I get back the z. So what's happening here? Inside my tensor structure, I'm keeping track of what? First the parents, x and y, then a pointer to this backward function, uh, which is called op, and it points to this tensor matimal backward. So you see, I know the operation that I applied, I know the parents. So silently what we're doing actually is we're building a directed acyclic graph, which is important for our computations, right? Later on when we apply some other function, like for example sum on this z, we'll be adding this sum to this list of operations, and z will also, the parent will be added into the parent. So silently we're building a graph, right, which is called directed acyclic graph. So backward is a little challenging. For example, we need to apply topological search on it to see to check each and every node, and we'll be our gradients, the calculated gradients, will be flowing back to all these nodes, and we'll be updating the values where required squared equals true. So I hope I'm able to clear the idea. So let's see, where do we need to make further changes. So yeah, this is my main tensor create new. Okay, let me just go ahead and be brave and take further steps um, to actually change our existing code. Previously we were working with this test file, and now I need to make the changes in our actual file. So let's go ahead and see what we have. Let's just do this. Yeah, and go in tensor edge, external tensor file, and put them all here. Yeah, perfect, 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 perfect. And let's modify the tensor create new as well now. Tensor.c, and new. Where is new? So all we need to do is t parents equals null, t operations equals null, t grad equals null, and t num parents actually 0. Perfect. So tensor create new, done. Let's go to the main file, main C, and looks like we are done with this thing. And now let's see the parameters that we are passing here in actual tensors. The implementation and main are same. So tensor create new, remember this is the function that we're using. It takes arena and dimension and shape. That's totally fine. So we've written this logic for Autograd as well. So for Autograd, perfect. Yeah, this should work. This should work. Okay, tensor randomize. What does randomize do? I need to check. Do I have to make any changes here? So tensor C, really. Okay, so tensor C. Yeah, randomize is does nothing, it just populates the data, so we don't have to be worried about this thing. This is fine. Size, tensor size, yeah, size is also work, size will also work. Tensor.c, tensor size, this should work because it just calculates uh, the number of elements, multiplies rows by columns, and we'll get the number of elements, right? Very simple. Where is it defined? Okay, size equals 1 and multiplies to shape, and if shape has like 3 dimensions, so batch size times sequence length times embedding dimension for 3 dimension, and for 2 dimension will be sequence length and embedding dimension. Perfect. No major issues seen so far. Let's just go ahead. Yeah, there is something here we need to do a lot of stuff. So first of all, tensor create new, this works, this code is commented out, so we'll be um, doing in the for stuff with this thing in the for loop and chunks. This will work fine, this line is okay. MHA create new, let's see what we have there. To see MHA create new. Okay, so it takes number of heads, sequence length, blah blah blah, arena log, this is fine, memory allocations is fine, we're using custom buffers, and then this thing is fine, this thing is fine. Create weights new. Okay, we haven't made changes in weights, so nothing is special. I'm just gonna go ahead and see tensor create new, and I'm just gonna copy this code and go to where and who's calling me. All right, so yeah, so yeah, tensor log, this thing is fine. Tensor create new, yeah, we copied this stuff, right? Here we were, so tensor create weights, I guess, new, and all I have to do is put them here. Yeah, yeah, fine, perfect. So we're supposed to go to ETN for MHA, MHA create new. Okay, fine. So using this, we modify the tensor create weights new function as well. And now weights new, this line will work fine. So okay, so far it's good, so far it's good. Okay, let's go back to the main. So yeah, till here we're okay. Initialize the parameter, let's quickly check out this as well. 2.c mha init parameters does nothing, random weights, yeah, it'll just be populating the data, so we don't need to change this as well. Okay, let's see what we have here. So what we are doing actually is we're trying to make this forward loop training loop work. We're going line by line. We're tracing back the entire code. We're going to those files which have created these, where these functions are defined, and if we want to see if any component, and by component I mean that if there is any tensor, Matimal, tensor softmax, if there is any forward or backward method, component method, and by component I mean that, you know, building blocks, you can say, needs to change for forward or backward. If not, we're just good. Okay, lir norm create, let's see this one. So ln.c lir norm create new, maybe. What it does has is features, allocates the space, tensor create needs weights. We're done with this, so it will automatically build. See the advantage. So it will automatically build the computations graph. So you see now the core foundation, everything boils down to the core foundation. The core foundation is tensor abstract. So everything is going towards the tensor class. So if you build your tensor class rock solid, things will be much easier for you later, because all it does is you just uses tensor. It just uses tensor abstract. So this is the advantage of using modular programming. Yeah. So tensor create weights new, this will work for now. uh, hat, x hat, and var. I think we need to make some changes here. Yeah, x hat and var. Okay, let's just quickly verify. Okay, I think I need to make some changes here because x hat and var. X hat is something that x hat is basically linear transformation, and var is basically variance. So I think these are the two weights matrices that needs gradients. So if they need gradients, then obviously there should be gradients matrices over here, initially defined null, and in backward pass we'll be actually working on them. Or if I see the definitely there will be something in the forward function in this layer norm. So layer norm forward. Yeah, so if you see arena allocate x hat tensor create new. Okay, tensor, we're done with the tensors. Yeah, row pointer, head row pointer, output pointer, took the mean, took the variance, uh, defined gamma and beta, and use this linear transformation to populate every row of y, which is our output. And okay, let's just verify this create method. So okay, mm, uh, hmm, mm-hmm, what's wrong? Chrome. Uh, all right. So Autograd computational graph. Do I need to change this method? Oh, I should not change this function for autograds, parameter creation, not a tensor operation. This is super important to complete the different worlds. Parameter creation. Okay, so we were wrong. I think we were wrong. Their norm create. Okay, let's not do this because it's basically saying the same thing which I said, so I was curious about these two. So it said that no need to change. Okay, fine, no worries. Main C. Alright, I'm gonna check create new, done, and target tensor randomize batch layer norm initialize parameters ffn create. Let's see what we have in there. um, ffn create, and it has tensors only, and that's it. No need to change nothing. Perfect. Main C, initialize parameters, layer norm create same initialize parameters, log information, and created the batch pointer for actual data, and created target pointer, and then define the shape batch tensor create. Now so far wherever tensor create or tensor matmul or tensor related operation, we're good to go. But I'm curious, where do I use tensor softmax? For that I'll definitely change. Need to write two methods. I need to write two methods for tensor matmul and tensor softmax. So tensor matmul I'll be writing forward and backward, and same for tensor softmax. So these are the two methods that are very important for now, and rest everything is based on them. Maybe transport as well, but I don't think transport doesn't change any doesn't mess up with any weights. So yeah, we don't have to do anything, I guess, with transpose, obviously. And then it just, it just mem copy on the same memory location for our actual target and actual tensor, and then a tensor score MHA forward. Let's see what it does. Okay, so here we are. It just creates target batch pointer and target pointer, target batch pointer, basically for um, actual data and target data. Okay, fine. It just defines temporary batch tensors and target batches. From big giant data, it just takes initial chunk, and maybe it will be some head sizes or whatever, and then check this code down, may have bugs. Okay, it doesn't have any bug, so let's remove this line. Okay, so yeah, let's see MHA forward. uh, uh, what this does, tensor matmul. Yeah, so just use forward here, and here too, forward and forward. Okay, so Q, K, and V. Yeah, we are using tensor matmul here, and we need to change now. Here, let's just go to tensor matmul, and let's rename it to forward first thing. Forward, and let's use our newly written method, which we wrote in previous tutorials. So tensor matmul matmul forward. Yes, here it is defined. Matmul forward. So parameters are the same. We don't have to change anything with the parameters. And yeah, this is our computation logic, and returns the output. And tensor dot c tensor matmul forward, and just use this new one, and just for a while just comment this out. Fine. Obviously we need to make changes with the headers as well. So yeah, I don't think I have to make any changes with the headers, because in header file the parameters are same, the output is same. Arena is in case if you wanna see it. So tensor h and tensor matmul. All you have to do is change the name here. Forward arena A and B. That's it. Fine. Main. Sorry. TN2 MHA forward. There we were. So yeah, done. Rows and columns, definitions, create new will work fine. Create new will work fine. Common shape. All it does is just appends the stuff. Okay, so scale dot production. Scale dot product. Where is this defined? Yeah, scale dot production takes A, Q, K, V, and T. Transpose. We'll check this later. Forward. Check this later. For Autograd. Okay. Forward. A, Q, K, T. That's fine. Alright, this logic is fine. Softmax forward and softmax backward. Check for Autograd. Let me just do first of all, which we have actually modified. So I'm doing I'm seeing only those methods which we have just modified and created the computational graph for, and I'll check these the rest of the ones later. So definitely I have to write the forward here for forward pass, and then we'll see for backward pass as well. Okay, that's it. That is it. Yeah, in case if I want to see the definition of tensor softmax. Okay, so should not use malloc first place. Should use arena lock. Arena lock, yeah. Let's just change this as well. Arena lock and data. Yeah. Data. So I should take arena to arena A, tensor T, fine, arena located. Okay. Yeah, size of tensor. It turns null. Use arena lock here as well with passing arena, and then we could have used n dimensions, but I think I'm not passing n dimensions here. Okay, let's let it go for now. This logic is fine. This logic is fine. This doesn't have to do anything with our okay, so okay, fine. That's it. No tensor minimal, nothing. Only tensor softmax. Let's just call it forward as well. Forward, and it just allocates the tensor, right? Fine, and it just defines the shape and arena. That's fine. Arena log takes the arena in size. That's fine. That's fine. Okay, rows loops back. For rows and columns, and just takes the maximum of the total data, and then subtracts the maximum over here, taking exponential. That's fine. Yeah, that's fine. So all we have to do here is forward. Yeah. So um, tensor C. Uh, tensor H. Really? Yeah. Tensor H. Where is softmax? This is now forward, and it takes as well. Let's go to main, or maybe 2.c forward. So we're done with MHA forward. We've made the required changes, so we're just writing this stuff down wherever we need to work. So scaled dot production, scaled dot product, and this only had one function. Now this is forward, and it also takes arena. Oh man, yeah, it also takes arena A. Fine. Return manual forward. Perfect. Yes. All right. So, let's see what else do we need. Image forward done. Clip gradients. Tensor C. It does nothing. So clip gradient just clips the gradients. Tensor size is used. Yeah. This is fine. Clip. Okay, so tensor check. Yeah. Let's check this as well. Tensor C. What it does basically, it has name and tensors. It just returns Dave if it's exploding. Okay. Yeah. L1 forward. Layer norm forward. And what this does, it takes layer norm, it takes tensor, it takes arena. Okay, allocate some space. Tensor create new will work fine. Okay, output tensor create new row and column. And I think we don't have to do anything special with it, except we need to create nothing, I guess. This is totally fine. This is like the previous observation, and let's just verify this as well if you need to make any changes with it. Uh, mm, okay. Alright, so I think we need to do some changes with this thing. So tensor create will work fine. Tensor create will work fine here, and so anything that is outside of tensor abstract, we need to see this. We need to take into consideration. Uh, mm, okay. Yeah, I think we need to do some stuff with this, and so we need to for all these mean and variance and everything, we need to make a separate functions using tensors, and we need to build computational graph on our way up for these tensors. So right now what we did actually is we are just calculating the variance sum mean and derive functions like this. So tensor mean, tensor variance, and even for multiplication and subtractions as well, in order to keep track of the gradients that are flowing through apart from these tensors. And then okay. Okay, so it seems like we need to do some stuff over here, because right now we are doing float maths, and we need to change it to tensor math. And what do I mean by that? I need to convert these float mathematical operations to some graph, some computational graph, and for which um, I need tensor operations. And by tensor operations I mean that, for example, let's see this thing. So we have x row. Row means this is a row pointer. So if we have 3 rows, let's say in a matrix, each row will be starting from the will have the address of the first byte, and the next will have the address of the second row, first byte, and third, and so on, right? So this is actually the x row. And what is x hat? So x hat is basically um, x minus means divided by square root of variance plus variance square, which is called standard deviation, and plus some epsilon, right? Some small value, in order to avoid zero division errors. And this is our y row, that is output matrix yth row, right? Which is going to be this. So for now we're using float. We need to use tensors over here. So I think I'll have to rewrite this entire layer norm method. Let me just go ahead and comment this out, and let me just write the steps what I actually want to do here. So so instead of float maths, we need tensor graph maths here. um, each let's say operation should have their own relative tensor. For example, mean, tensor mean, and what else? uh, Tensor mean, tensor variance, and tensor subtract etc row wise, right? Row wise. For example, if this is my uh, if this is my tensor 1 2 3 3, let's say 4 5 6, and let's say 7 8 and 9, let's say this is my tensor. So this is going to be my first row, this is second row, and this is third row. So we'll be taking mean, standard deviation, variance, everything row wise, right? For example, if I'm to calculate the mean of this thing, I'll be taking this value divided by the sum of all these values, right? So this will give me the mean at this particular index. So row mean would be something like yeah, so row mean, okay, so let's just see from here. Yeah, this is mean, so x row divided by column. So row, sum of row divided by number of columns. Sorry, this is not actually the first element. Instead, it is sum of this entire row divided by number of columns. So that's what we have. All right. So then similarly for all the other operations, and then what we will do is create computational graph using tensors. Yeah. So we need to do these things here. So first thing, tensor mean. Second, tensor variance. Third, tensor add. Fourth, tensor sub etc. So we'll be doing we'll be writing these operations like these. So similarly, we'll have our tensor.h update as well. So let's just write here. So tensor mean, it's gonna take a row pointer and what, columns, right? And this is going to, columns are going to be our embedding length or whatever. And similarly for, and this is gonna return what, yeah, this will return tensor. Should be a pointer? No, I don't think for now, but we'll check this later. So tensor mean and tensor add, and it's gonna take row, and what add is gonna take. So let's just check. Tensor okay, So what is this scaling factor? Okay, so mhm. Yeah, so this will be like uh so let's say if y equals x plus z equals x plus y, then z is the product of two vectors, but here we are taking rows. So I think this should also be a row pointer of first, and then row pointer of second matrix, maybe. Yeah, but we'll check this later. We'll make a separate video on this. Let's just have intuition of how things are gonna work now. So mean add tensor uh, uh, tensor sub, and it's gonna take pointer to row 1, row 2, and we'll have whole other um, methods over here. So let's just see uh, forward. Okay, so layer norm. Yeah, so these are all the things that we're gonna do right now. So what we'll have after these, we'll be having a tensor specific layer norm forward function in which all the operations will be having their own tensors representing the operations instead of just writing the straightforward code like we did here using for loops or stuff. And we'll be calling tensor functions which are going to do these operations for us, and then we'll have uh, a kind of like modular layer norm forward method which will be having mean, variance, and everything, right? So we need this for our Autograd to generate a computational graph, because in computational graph or Autograd world, there's nothing called float operations. Everything is inside tensor operations. So this was actually the key idea of Autograd, right? For now, let's keep this function as it is, and we'll implement this later. And let's see what we have in our main.c layer norm forward. Here we were. Okay, so ffn forward. Let's see what we got here. Phi ffn. Okay, so we have tensor mapmul. This should be forward. This should be forward. ReLU. This is ReLU forward, so we need to change ReLU forward and ReLU backward as well. So let's see where is ReLU for now. Uh, so we have two functions related to ReLU in particular. So ReLU forward is there's nothing, no such thing called ReLU forward. It's only ReLU. So we need to give it a name ReLU forward and ReLU backward. So let's just check where this ReLU is. So this is going to be in feed forward and in dot edge. So let's just check ReLU. There it is. Let's call it forward, and it should take arena as well. And let's see if it it just uses some space or not. If it uses some space, then we're gonna pass arena over here. So okay, so ffn ReLU, where is this defined? Yeah, ReLU. It doesn't do anything, so we don't have to do anything with this. Yeah, no arena, nothing. Fine. Let's just call it ReLU forward. ReLU forward. We've already called it ReLU forward, and then ffn.c Where is ReLU? Okay, so forward. Yeah, so this is ReLU forward. Later on we'll be writing a function called ReLU backward, and this is going to be tensor matmul forward. And yeah, everything is fine. Rest of everything is fine. Perfect. And what changes did we make here? Okay, so if in case if I made the changes in the header file as well, really forward, perfect. Let's go to main. FFN forward, layer norm forward. We'll write this later. And tensor MSE loss. Let's just check this thing. Tensor MSE loss. Tensor create weights new. Okay, fine. Pred data. Yeah. So grid. Okay, so it just returns. It just takes the gradient and returns the gradient, which is actually the derivative of this loss, I guess. So what do we need to do with this? So you know what happens? Let me just tell you. Let's just think about it. Where's my sketchpad? Okay, so what happens is basically, what happens is I have a forward pass which works something like this. So this is actually a matrix of my input. This goes to positional embedding and token embeddings and some of them and everything. This goes to something called MHA, and has its own activations and everything, activations and projections and tensors and whatever. So then it goes to a layer norm. Then this goes to FFN, feed forward neural networks, and then we have another block of layer norm, right? And there's some residual connection over here as well, which we haven't implemented, mind you, for now, but we'll definitely implement that later, inshallah. And this is my layer norm, and after that I have loss tensor, and this is exactly of the same shape as this X was, right? Loss tensor. So now we need to compute the gradient of this loss with respect to these parameters, right? Using chain rule, and this goes here, and this goes here, and this goes here, and this goes here, and everything, right? And then we keep on just updating the parameters, our derivative parameters, d loss over dw, right? And then we keep on adding these. So here what we did is we have some our prediction, whatever our model computed, and the actual target tensor, and then we have created a temporary gradient tensor in which we'll be adding or populating the actual derivatives of this loss, right? And this is actually our loss gradient, that's right. So we have a size, and then we went ahead and applied the formula. So in case if you find the derivative of mean squared error, so that's going to be like mean squared error 2 times this minus this. Yeah, this is correct. So this is actually the derivative of loss with respect to the parameters, and it's just populating and returning this gradient. But this should be done using our loss backward function, right? So that loss backward should return us a tensor of gradients, nothing else, right? So this should be loss dot backward, right, instead of just loss. And then we'll see this later how we can tackle this, right? So yeah, I think the video is very already very long. So that's it for this lecture, and we'll come up with the next one to do two things. First thing, implementing layer norm from scratch, implementing all those mandatory functions, which creates us forward computational loss, computational graph, and then for backward, we'll see later how to tackle this. So that's it for now. I'll see you in the next one.